Hi everyone, my name is Johannes Englsberger. Here I'm presenting to you our RSS 2020 paper, MPTC, Modular Passive Tracking Controller for Stack of Tasks-based Control Frameworks. This is a really beautiful control framework, which I recently created with my colleagues listed here. All of us working at the German Aerospace Center DLR. Having an arbitrary robot at hand, may it be free-floating or fixed-base, the basic idea is to assign various impedance-based controller modules, the so-called Modular Passive Tracking Controllers, to different parts of the robot. The corresponding tasks may, for example, be formulated in Cartesian or joint space. Now the different control objectives are combined into a stack of tasks, which is basically a mapping from the optimization variables via the stack of task mapping matrices to the stack of task vectors. Now the stack of tasks is solved via an optimization. So, for example, using a pseudo-inverse or a quadratic program. And the most critical point is that the overall controller synthesis is passive, if possible at all. In contrast to inverse dynamics, MPTC is not only nice in theory, but also in real-world settings. In the following video, we will see our humanoid robot TORO walking based on MPTC. It is quite remarkable that this experiment has been taken just a few hours after trying the controller for the first time on real hardware. At this point I need to stop the presentation for a short timeout. If you prefer a presentation of figures and videos only, just go on watching this video. If you're interested in the basic math behind MPTC and maybe want to prepare for our discussion during the poster session, please follow this YouTube link for a more detailed presentation. Now I'll be presenting a bit of an overview and some really nice results. MPTC covers the complete range in between inverse dynamics on the one side and PD plus control on the other side, depending on the granularity of the targeted decoupling, or in other words, on the desired modularity of the tasks. Here we see the results of a fixed-base robot simulation, showcasing the regulation case. Note that the overall Lyapunov function V never increases except for discrete events or in case of perturbations. Here we see a fixed-base robot regulation scenario for an overdetermined controller setup. Note that the subtask Lyapunov functions may grow, while the overall Lyapunov function is guaranteed not to grow. Next, to showcase MPTC's ability to control floating-based robots, I present the result of a simulation of TORO walking in OpenHRP. Except in case of perturbations, we observe precise trajectory tracking, both for the center of mass, or here DCM, and for the feet. The results of the walking experiment that we had already seen are shown here. Again, we observe decent trajectory tracking. It is important to point out that MPTC, as compared to inverse dynamics, requires a very low tuning effort when it comes to its real-world application. The overall control framework of TORO, in addition to MPTC-based tasks, also contains an angular momentum regulation task. Here we see the achieved robustness. Another very important criterion for robot controllers is safety. As you can see, using MPTC allows to safely interact with complex robots. TORO is actually quite huggable now. This is the end of my talk. I thank you very much for watching and hope to see you at my poster presentation.